So this full adder we can implement using half adder.
Yes.
So then what is that we require to know is this half adder itself. So half adder has got a B, sum and carry out. So
Yeah.
then we know that with the two variables, given two variables or n variables, we can have 2 power n possibilities.
Yes.
So this 2 power 2 here, this because we have these two variables here. So total
Yes.
possibilities. Those four possibilities are 0, 0, 0, 1, 1, 0, 1, 1. So they are for AB. And
Yeah.
we go for sum and then we go for carry out. So here
Yes.
this result is 0, this result is 1, and this is 0, and this is 1, this is 0, and this is 0, and this is 1. This is how this binary addition is performed.
Yeah.
So now from
Binary 1 bit addition, right?
binary
1 bit.
1 bit. So this binary 1 bit addition. So now from here, if you want to implement this sum wherever this output is 1, corresponding to that, if you see these variables here, then we can develop the Boolean expression required for the sum. So either this should happen like A bar B or this should happen A B bar.
Yeah. Yeah.
Similarly, CO can be written like AB. So when these two are 1, then only it is like output is 1.
Yeah. Yeah.
Now from here, we say that to build this one, I require one NOT gate here, and to get this B bar one another NOT gate, and then to perform this A bar B, I need one AND gate here,
Yes.
NOT gate, and here also one NOT gate, and here one AND gate, and then to build this final expression, we need one OR gate.
Yeah.
So here we say that we require one AND gate. So that's how we build this one.
Yeah.
Now we go for this one, that is full adder concept. In the full adder concept, again we have to understand like mm, this has got A, B, and then there is a C in, carry in, and
Yes.
then this is sum and CO, carry out. So this is like if multiple bits if we are adding. Uh, so in this case, here we can implement using, because 2 bits we can implement using half adder here. But
Yeah.
when we have this kind of like multiple bits here in the operand, given operand, then a carry may generate from the first stage, and this carry may go to the second stage here.
Yeah.
So at that time, including this carry, we had to perform the addition.
Yeah.
There were the concept of full adder is.
Right.
So now what we do is again we build this A, B, C in. Then the possibilities are total 2 power 3, that is total 8. So 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, and then 1.
Mm.
This is 4, 5, 1, 0, 1, then this is 6, and this is 7. The
Yeah.
custom is to start with 0, so we end up
Yes.
having 7.
Yeah.
That way it is like total, 8
8.
combinations.
Yeah.
So now from here we build this one, that is the sum and this carry out. So here it is 0, here it is 1, and this is also 1. Here we may have the carry because 0 plus 1 is sum is 1. 1
Yeah.
plus this 1. So leading
Yeah.
to sum to 0 and carry 1. And here it is 1. And then this is 1 plus 1. Sum is 1. 1
Yeah.
plus this 1 when we do the sum plus this 1. So leading to this sum 0 carry 1. So 1 plus 1 again here the sum is 0 carry out is there. So the sum
Yeah.
plus this 0. So that is it's here 1 plus 1. So leaving the sum 0 carry out 1. And the
Yeah.
sum 0 plus this 1 is leading sum 1 and the carry is anyway there.
Yeah.
So just a minute. No, 1 minute. To wait. So
Yeah.
here you have this some I mean carry 0 and here also carry 0 and
Yeah.
also carry 0. Here also carry 0.
Yes.
So now what you do here is to get this sum expression, you go with the K-map expression instead of direct observation here. Even
Yeah.
direct observation also possible. The way
Right.
the way here we did the for smaller things, direct observation is enough.
You're right.
But when number of variables increases, in that
Yeah.
case, we may have to take the help of either this K-map or another thing is this one. This is fine.
Yeah.
Markless.
Right.
Or this is also known as a tabular method.
Okay.
So this we have to use when number of variables increases more than 5.
Okay.
So, but now we have A and then B, C in. So here 0, 0, this one, 0, 1.
Yeah.
And we cannot go with 1, 0.
Yeah.
And then we are to have 1, 1. It is not allowed this way. It is
Right.
only one
Yeah.
variable change must be there.
Yeah.
So it can go from here to 1, 1.
Right.
And then it will go to the 1, 0.
10. Yeah.
So here you have this 0, 1. Now, this minterms, if you look at this decimal equivalent, them we have to put here for easy, like, for this 0, 0, 1 is 1, and this is 0, 1, 0 is 2, and this is 3, and this
Hmm.
is 4, and this is 5, and this
Yeah.
is for 6, and this is 7. So
Right.
one way is to have these variables here like this, and
Yeah.
then put like what possible values this variable can take like this, or
Mm.
straight away put here a bar, straight away put here a, and here instead of putting this one, you put b bar c in here, and
Yeah.
put here b bar. This is b bar c in, this is b bar c in bar, and
Yeah.
this one is BC in, and this one is BC in bar. So
Yeah.
that way also, some textbooks we see that way, like they don't keep like this here. They directly put
Yeah.
here this way, and some in some books we see here, variables keeping here this way, and what
Yeah.
this it takes like that. And then, this now we can, instead of each time like combinations of ABC in observing, we straight away check this decimal equivalent. For that decimal equivalent, we already have kept the cell number here. This is the cell number that
Yeah.
we kept. So
Yeah.
at minterm 1, at minterm 2, at minterm 4, this 2 and 4 and at 7. So 1,
Yeah.
2, 4, 7. So one is here, 2 is here, and the 4 is here, the 7 is here. So
Yeah.
there where we have this sum 1 here.
Yeah.
So now only is the thing is grouping here. So grouping
Right.
rules are there in K-map. We have the grouping rules.
Yeah, that I know. You
Okay.
can skip that part.
Okay. So now here, based on that grouping rule, what we do here is these two are adjacent. So we group,
Right. Yeah.
and these are also adjacent, but diagonal is not permitted.
Yeah.
So that's why we don't group these two.
Right.
So what we do is this extreme corner, if you fold this graph, I mean this map,
Yeah.
this end and this end will come adjacent to each other.
Yeah.
So that way these are like, we can group them.
Yeah.
Now what we have here is like in this, if you see here, this is A bar, this
Yeah.
one. And here in this common is, if you look at this one, 0 and here 1, no common
Yeah.
variable. And this is
Yes.
1 and this is 0. Again, no common variable.
Yeah.
So then, so we put a plus and then we come to this one, this end and this end.
Yes.
So this is A and we check here, is there any common in this?
Yeah.
There is no common. We made some mistake. That's why we are ending up having this kind of expression.
Yeah. I think that one and that reversed basically.
So we made some mistake. That's why we ended up having this one.
Yeah.
Reason for this mistake is, and here if I look at this 0 and 1 0, it is leading to the 2.
Yeah.
So but I supposed I would have considered this one.
Yeah.
So that is the mistake.
Right. Right. Yeah. It will be
Huh.
reversed.
So now what we can do here is we can build another thing here. 0 0 0 1 instead of 1 0, now 1 1 1 0.
Yeah.
So this is your A, this is B, C, N, this is 0 1. So now if you look at this one here, this is let us put the cell numbers here directly, 0
Yeah.
1
Two, one,
3.
three,
This is your
two.
2,
Yeah.
and
Yeah.
this is
Now.
your 4, and this is your 5, and this is your 6, and this is your 7.
Yeah.
Now here 1 2 4 7. So 1 is here, 2 is here, 4 is here, 7 is here.
Yeah.
Now you cannot group these two because they are not adjacent, and
Yeah.
these are not adjacent, and these are not adjacent. So
Right.
here, this one individually, this one individually,
Yeah.
this one individually, this one individually. So
Right.
here, this is, implicant, one implicant, like four implicants here.
Yeah.
So now here, if you write the sum expression, sum equal to, now you can write here A bar, this A bar, and
Yeah.
here this one is a B bar C in plus,
Yeah.
plus is a logical OR,
Yeah.
not arithmetic addition, this one.
Yeah.
So now here this one is A bar and we have B C in bar.
Right.
And then this is again logical OR. Here we have A and then B bar C in bar
Right.
plus now here we have A B C in. So now what we have to do is we have to see, is there any possibility of minimizing this, that we have to check. So
Yeah.
if you check this, A bar to take out common, B bar C in from here, and from here B C in bar.
Right.
Now here if you take A common, now you can write B bar C in plus this B C in.
Yeah.
Now we have something called this A XOR B, A XOR B. These are the
Yeah.
standard symbols.
Yeah.
So this tells us that A bar B plus A B bar, if you expand this one. And this one tells us A B plus this one. Maybe in case if we are not sure whether this one or A bar B bar, Then very simple thing is this is anyway X NOR.
Yeah.
So this is your X OR.
Yeah.
You get X NOR if you complement the whole thing, this one.
Right.
So if you complement the whole thing means like A plus B, if you complement according to De Morgan theorem, you can write A bar dot
Yeah.
B bar. So
Yes.
in that case, this is your A. So what you can
Yeah.
write here is A bar dot, and this is your B.
Yeah.
So this, sorry, this one is just a minute. This one is bar A dot B bar, this whole bar.
Yeah.
Now from here we can further this one
No.
internally according to De Morgan again, if it is AB bar, then A bar plus B bar. So now
Right.
this seems like AB, so we can write A bar bar plus
Yeah.
this B bar
Yeah.
dot, and then here A bar plus B bar bar. Now
Okay.
bar of bar, inversion of inversion is again true form.
Yeah.
So this is like this, and here A bar, and this inversion of inversion is true form. So from
Uh, in the
huh,
in the A bar whole bar, will it be plus, right? The first from where the arrow comes.
wait 1 minute. Huh? One,
The next, yeah,
but
the
one
next, yeah,
minute, one
this
minute,
one.
1 minute. Which one now?
Number two.
Number two,
Instead of dot, it will be plus, right?
this dot.
Oh no, no, yeah, okay, the bar is gone. Okay, yeah, correct.
Here is a dot.
Right, right. Okay, yeah, no, no,
Dot,
yeah, no,
this
I
dot
got
is
it now.
different. This
I
dot,
got it.
this dot has
Yeah,
come
yeah, this is it.
from here.
Okay,
This is your C plus D, let us say.
okay,
C plus D has got whole bar here.
yeah,
You can write according to this first law,
right.
this C plus D whole bar if is there, you can write C bar plus
D
C
bar,
bar, sorry, C bar dot D bar.
D bar, yeah,
So that's what
got
we
it.
have done. This is your entire thing is C
Yeah,
dot,
yes,
this entire thing is your D.
yes,
Got it?
yeah, okay, yeah, got it. I got it.
So now if you expand this one further, A dot A bar, then this is your AB, then this is your A bar, B bar, then this is your B bar.
Yes,
This leads to 0.
yeah,
So we have here AB, this AB, and we have here this A bar, B bar, this A bar, B bar,
right,
and this is 0. So
yeah,
the conclusion is this X nor here, what I have written is not correct.
yeah,
Last one. So this
yeah,
is supposed to be AB plus A bar B bar.
yeah,
So that way you can cross verify in case
yeah,
somewhere if you have messed up.
yeah,
So now if you observe this one here, it is resembling like that only. The common thing that we have taken from here, where is that? Here, if you look at this one,
yes,
it's like A bar B
yeah,
plus A B bar.
yeah,
So it means what you can write this one as a B XOR C in.
yeah,
Okay.
yeah,
Plus this A is there anyway, but here if you look at this one, this is like AB plus this A bar dot B bar, na?
yeah,
So it means what this is actually A X nor. This is X nor.
yeah, yeah,
So now this X nor, this expression you also can write A X or B bar.
yeah,
So it means here we have instead of A, what we have here is B X or C in whole bar.
right,
So now again, if you look at one, two. 3. The third one, if you look at,
This
so
is
here it is like A bar, this whole thing is B, and
yeah,
here A, and this whole thing is B bar.
yeah,
So that leads to the final expression here, A bar XOR B bar.
yeah,
B bar
yeah.
plus we have this B XOR C in.
And yeah,
So that way we are getting the expression. This is A actually. This is not
yeah.
A XOR B bar. A XOR B XOR C in.
In yeah,
So that's how we are, getting the expression for the sum.
yeah, yeah.
So that is how it is. Just a minute. No, where is this? View. Now, similarly, we work for the C out also.
Yeah,
So when we have this kind of thing, that is about
same.
that is about the full adder. Now
Yeah,
this full adder expression, if you write, let us write that we because we got to know that this sum is A XOR B XOR C in, and this one CO. Let us very quickly work out for that also because we wanted to present something. So that's why we let us work. A,
yeah.
B, C, and 0. This is 1. This is 3. This is 2. And this is 4. This is 5. This is 6. This is 7. So now
Mm.
simply if you go to the table here, we have a 3, 5, 6, 7.
Yeah, 3, 5, 6,
So
7.
3, 5, 3, 5, 6, 7.
Yeah,
Now they are adjacent here, this two and this two and
yeah.
this two. So
Uh,
now all are essential prime implicants only.
yeah, yeah,
So now here if you write for this essential prime implicant the product term, so the
yeah.
product term will be A and the common here is uh, you
Yeah.
have C in.
Scene, scene. Yeah.
Now if you write for this
Okay.
that is B C in
Yeah,
because here this is differing you don't include.
yeah, yeah.
Now, if you write for this, then that is
Yes.
A, and the common
A
here
and
is
B.
B. So
Yeah,
now you have here A, C in, A, B, and B, C in.
right.
So now from here, what we try is there any possibility of taking out like that? If you see this AB, if we write here, and C in if we are taking out A plus
Yeah.
B. That way we can write.
Okay.
This CO, this AB, I wrote it down here,
Yeah, yeah.
and it C in here common.
Right.
So I took out this one, and A and B are inside the parenthesis.
Yeah, yeah.
So now if I put this sum as underneath here, this is actually one sum. And this, if you look at this, is actually one carry out.
Okay.
So
Yeah.
now what I can do is here I can put here one half adder. I can give here A, B. Now I can get this sum here and let us call that sum as S1. So I am calling
Okay.
it as a S1.
Yeah.
Now this is the carry I'm calling as a C1.
Okay.
Now to get this actual sum, what I am doing is this S1 is actually XORed with this carry in.
Yeah.
So it means what I require another half adder
Right.
This half adder takes S1 and another input as a C in.
Yeah.
So then it produces for me some actual sum.
Yeah.
Now this half adder also produces one carry out.
Yes.
So that carry out I'm calling it as a C2.
Yes. Okay.
So now what I have to produce here is this just a minute. This AB anyway is it has given already C1 this AB.
Yeah.
But what about this portion here? Somehow I have to manage this one. Na?
You're right.
This one I have to manage. So if you look at this C2, what is this C2 is all about? Let us work out on that. So if you work out on that, C2 here is we have C2. We need C2. So C2 is actually this is like this S1 is like A for this and
Yeah.
B for B is C in actually this C in.
Yeah.
So that is so C2 generally we in the half adder it is like A dot B.
Yeah.
So A dot B means A in the place of A I have S1 dot
Hmm.
in the place of B I have C in.
Yeah.
So now this S1 is A XOR B
Right.
and C in.
Yeah.
So now if you look at here this one mm, this carry out still we have to work out now we have
Yes.
to get something like this is a logical OR here we have logical OR
Yeah. Yeah.
and we are getting here this is XOR.
Right.
So then we had to work out. So what is that we can do here is, let me rewrite this one. CO equal to AB, um, this AB, AC in, BC in. In this AB, no issues with that, and this CN also no issues. Only this is the thing. So
Yeah.
here we have the logical OR. Now somehow this logical OR at this place we somehow we have to show that these two are equal.
Right.
One thing is these two are equal. The other thing
Yeah.
we have to somehow obtain from this. That's the only way. Like these two are same. Like
Yeah.
but they are not same. Zero zero.
Of course. Yeah.
1 0 1 1 this is 0 this is 1 this is 1 this is 1 but the
Yeah.
truth table of this is a plus b
Yes.
this a XOR b is different
Yeah.
that is 0 this is 1 this is 1 this is 0
Yeah.
this is the table for that so now what is that we have to do here if you if we are ORing these two like C1 and C2.
Right.
Let us OR these two. If you OR these two, what is that? At the C1 we have AB C2, you have this S1 dot C in.
Yeah.
Your S1 is AX or B dot C in.
Yeah.
So you have this C1 plus C2. That is logical OR if you are doing here.
Yeah.
Logical OR. Then you get this AB, AX or B, then C in. Now let us expand this one here. Uh, AB, this is A bar B, this is A B bar,
Yeah.
then C in. So you have here AB, A bar B, C in plus A B bar C in.
Yeah.
Now, what is that we can do here? Is there a way to simplify any Boolean law that you can apply? So
Um,
our main task is this AB anyway is their product term, but here we have to somehow some Boolean law we have to apply, and we have to get that
yeah.
this is A plus B C in that type we have to
Yeah.
get it.
Yeah. Which is possible, right? Like
So
A's or B, and then bracket, and then C in.
mm, you want me to you tell me what is that I have to write?
Yeah. C in,
C in
bracket open,
uh,
A's or B.
A X or B.
Yeah.
No, no, you're not getting my point. Then we are going back to this one only, na?
Ah, okay. Oh,
We
okay. You
don't
want the
want to
other way.
go back there.
Okay. Okay. Then uh, this is AB. Then we can. What was it? This AB. C. Uh, Sum plus C in. Didn't we get this similar thing? AB. Uh, like we are using just the second two equations, a part of the equation, or first also the
No,
AB also.
no, I will tell one.
Okay.
Our task is we have to implement this full adder
Right.
using two half adders.
Yeah.
So we give here AB and it performs addition, sum we get and carry out.
Yeah.
We give this S1 here to the second half adder. This is one half adder. This is second half.
Yeah.
This is going to give us the actual sum.
Yeah.
And this is not going to give us the actual carry out.
Yeah.
This is going to give us the C2.
Yes.
Now what we do is we perform the OR operation.
Yeah.
This C1 we give here, this C2 we are giving here.
Right.
Now this will give us the CO.
Yeah.
So what is that we have done here is S1 we already know
Yes.
earlier worked out here.
Yeah.
This one. This is
Yeah.
S1. So S1 this A bar B plus AB bar.
Yeah.
So that is nothing but A XOR B.
Right.
So that is A XOR B, and that is also like A bar B, A B bar.
Yeah.
C1 also we know that earlier we worked. This is AB.
Yeah.
Now coming to this sum.
Mm-hmm.
Sum is again here, since it is a half adder, and half
Right.
adder input is S1, and the other input is C in.
Yes.
So then we are substituting this A XOR B.
Okay.
Then we are putting this as it is.
Yeah.
So there are no issues with that.
Yeah.
Because when we worked out a full adder truth table, then we got the same
Yeah.
somewhere here.
Yes.
So now the issue is to address, we have to address this CO also.
Yeah.
So to address CO, now we have to, we know that C2, what C2 is.
Yeah. In the diagram, in the second half adder, what is the second input?
That is C in.
Okay. Yeah. Okay.
So this is C in.
Okay.
So now
Yeah.
from that, this is second half adder, this is first half of adder.
Right.
So this is second half adder. So second half adder C2 is like there A is S1
Yes.
dot the B is C in.
Yeah.
So if you substitute again this S1 here, that S1 is A bar B plus
Yeah.
A B bar
Yes.
and dot C in as
Dot
it
C
is.
in. Yes.
Then what we are doing is we are going to CO carry out.
Yeah.
So carry out their C1 logical or C2.
Yes.
So then we are substituting what C1 is. C1 is AB plus the C2 is this A bar B plus AB bar this into
Yeah.
CN.
Yeah.
So, but my question to you is CO we worked out
Yeah.
from the K-map
Yeah.
from K-map. So from K-map we got AB AC in plus BC in.
Yeah.
And this one, if you take out the C in common here, you have A plus B.
Right.
So now the question is, from the K-map we got this one.
Yeah.
But from, this is what from full adder using two half adders, we are getting this one.
Right.
In this, we have to justify that anyway, this part is here same it is.
Yeah.
And even this part is also here.
Same. Yeah.
Only this part is different.
Different. Yeah.
So somehow we have to prove, na?
Okay. Yeah, this is equal to this.
So that one is the task.
Okay. Uh, same. Mhm. Can this be same?
You can browse and you can tell.
Okay. Second, let me check. If I take yeah, now if I take a common, like I'm talking about the three operation in between, excluding the C in.
No,
So
no.
B, yeah,
Listen, are you telling this? You just acknowledge, okay?
okay.
So
No, I think I got it. If I can tell.
no, no. That's what what you are intending. I will put here.
Okay,
I will put here. If whatever I have put, are you intending the same? Just acknowledge that I'm telling.
okay, okay.
So this is
Mm-hmm.
clear, na? This part.
Yeah, yeah, it's clear.
If this is clear, then the in the OR this OR operation that we are doing is this one part, right?
Right, right.
The other part is you have the C1, right?
Yes, C1.
So now this part is C2.
Right,
So what this doing is this OR gate doing is C1 plus C2 it is doing.
right.
So C1 already I know AB it is.
Yeah,
Now the C2 is this one.
right.
This means AB plus A bar B plus A B bar.
Yeah,
So here now I have this C in here.
Right.
So from here, if I could able to take out this AB common here, 1 plus C
Right.
I can write here.
Yes.
And this portion I can write A XOR B C in.
Yeah.
And this is 1.
This is one.
This
Yeah.
is AB plus A XOR B C in, right?
Yeah. Yeah.
Are you trying to say the same?
Something similar, but in a, I was trying to equate AB
No,
plus
no.
A bar.
In that case, you try on your paper there.
Okay.
Whatever you are thinking, the way now I presented na here this way.
Yes. Yeah.
To do it, are you getting this one? You just see.
Okay.
If you are getting this one, then you are correct. If you are not getting, then you are wrong. You have to follow what I said.
Okay. Okay. All right.
Please do take time and do it.
Yeah. Yeah.
Here, when we worked using K-map for CO,
Right.
we got AB plus AC in plus BC in.
Yeah.
And when we further simplifying this Boolean expression, we are end up having AB plus C in of A plus B.
Yes.
But when we are trying here, the full adder using two half adders, we are
Yeah.
saying that the first half adder sum is given to the second half adder as an input,
Yeah.
and the second half adder is taking carry in as another input,
Yeah.
and it is producing sum and carry out.
Yeah.
This sum is the actual sum of the full adder itself,
Right. Right.
and the carry out is not the actual carry out of the full adder.
Yeah.
But we have to give this carry out to the OR gate, and the first carry out of the first half adder also needs to be given to the OR gate.
Yeah. Yeah. Yeah.
But when we talk about the C2, what C2 is? C2 is this one.
Right.
So this expression means A XOR B.
Okay. Yeah.
So this A, when you are clubbing this like logical OR, C1 plus
Right.
C2, C2 is actually C in dot this A XOR B
Yeah. Yeah.
plus C1 is AB,
Yeah.
this C1.
Yeah.
So this expression is not matching with what we have obtained using the K-map
Yeah.
here.
Yeah, ma'am. Yeah.
So my question was how we can prove that this expression is equal to
This one.
this expression,
Yeah.
this expression here,
This one. Yeah.
this expression, this one.
Yes.
That was the question.
Okay.
For that to prove that one answer is, let's say result one, result two.
Yes.
In result one, we have three variables A, B, C. In though the form is like true form and complement form, that is different issue. But the actual names of the variables are A, B, C in.
Yeah. Variables inputs are same.
So these three variables can produce total eight possible cases.
Yeah.
Here in result two also, these three variables can produce eight possible
Yeah.
cases.
Yeah.
So for every possible case, obtain the result one, what the result one output is, what the result two output is,
Yeah. Yeah.
R2 output is.
Right.
See that in both cases it is same.
Yeah.
That is one approach to prove.
Yeah. It's a long way. We have to calculate each eight possibilities and compare with the other one.
Ah, ah. The other way is to use the Boolean law.
Yes.
So this Boolean law says B plus B bar is equal to 1.
One.
So we are using that formula here. A into, that is A dot of
Yeah.
B plus B bar.
Yeah.
That plus B dot of A plus A bar.
Yeah.
So
Yeah.
it means this is one only, na?
Yes, yes.
So you are having A plus B only, na?
Yeah,
So
yeah.
from this, what we are doing is we are expanding this one simply.
Expanding. Yeah,
So if you expand this one, you are ending up having AB plus A B bar plus
yeah,
A bar B
yeah.
into C in.
Seen, yeah,
So now we got one part of that A XOR B is there anyway
yeah.
here.
Yes,
But addition to this A XOR B, we are having this AB also now.
yes, yes.
But somehow we have to get rid of this AB, na?
Right.
So now what is this entire expression is? Entire expression is C2, na? This is C2, na?
Yeah, C2.
So this C2, we are applying it to this OR gate, na?
Yes.
Along with the C1.
Yeah.
C1 is AB, na?
Right, right.
Plus C2 is this entire expression, na?
Interacting. Yes.
So this entire expression when I am putting and when I am trying to expand this C1 plus C2 here, this
Yeah.
expression.
Yes.
So from this expression, AB will be there anyway, plus
Right.
this AB into
Entire.
C in.
Yeah.
If I am taking out separately, if I am writing, from that AB I can take out common, na?
Yes.
AB of 1 plus C in, na? This 2.
Right. Yeah. Which
And this
becomes
plus and this plus and this entire part I am keeping separate, na?
okay. Yeah.
No, this you got, na?
Yes, yes, yes.
So now from here, what I can prove from here, this 1 plus C in means 1, na?
Yeah.
Again,
Yeah.
this Boolean law is there.
Right, right.
So this is now this AB dot 1 means AB, na?
AB. Yeah.
Plus A XOR B. This one, this is A XOR B, na?
Yes.
So what we have taken is A plus B we have taken,
Mm-hmm.
but we could able to produce this A XOR B.
Yeah.
So now this is another way of proving that
Doing. Yeah.
this expression is
Is
equal
same.
to this expression is equal to
Yeah.
this expression.
Yeah. Got it.
So now for that reason, this block diagram is valid.
Right, right.
That is what our
Yeah.
conclusion.
Yeah.
Got it?
Understood. Yeah, yeah. Got it.
So this is now what we have to do is in coming to the since we have to go parallel, what
Yeah.
we do is we stop this discussion. We jump to the Verilog part now.
Very long. Yeah.
Now in the Verilog, we have this 1 minute. Please. Here there are various ways to describe
Yeah.
1, 2, 3, 4, 5. Five
Okay.
ways are there to describe the hardware.
Isn't there three ways like gate, behavioral, structural, and mixed?
No, no, listen. Li-
Okay.
So describe equal to model. Okay.
Yeah.
So often we say that this is modeling. We keep saying no,
Yeah.
there are modeling styles.
Yeah.
So what we mean by modeling style means describing styles.
Yeah.
So the very basic lower abstraction level is switch level.
Right.
In switch level, we have keywords like NMOS, PMOS,
Okay.
CMOS, like that keywords are there.
Yeah.
So them we make use and we build any big circuit
Okay.
with the
This I didn't know.
help of PMOS and CMOS.
Yeah. Yeah.
You can build anything, na?
Yeah. Yeah. True.
For example, I want you to come up with a inverter
Yeah.
in CMOS technology.
Yeah.
So what you do, you keep your pull down section with NMOS device,
Yeah.
your pull up section with PMOS device.
Yeah.
You short these gates
Yes.
and you connect source of the PMOS to VDD.
Yeah.
Drain you short here.
Right.
You take the output Y.
Yes.
You give the input here, and the source of this NMOS is given to the ground.
Grounded. Yeah. Grounded.
Now,
Yeah.
this part is in Verilog HDL. It is like a NMOS keyword is there.
NMOS. NMOS. Yeah.
In Verilog HDL, for this PMOS keyword is there.
Okay.
So these keywords, if you are using and
Mm-hmm.
describing anything, that is called switch level modeling.
Okay.
So this switch level modeling is not supported by the synthesizer.
Ah. Okay.
Now comes the gate level modeling.
Right.
In gate level modeling, you have all primitives. You call them primitives.
Okay.
You have keyword and or nor,
Right.
XOR,
XOR. XOR. Yeah.
XNOR, not, buff, buff
Okay.
if zero, buff if one,
Okay.
not if zero, not if one, like that, several keywords.
Yeah.
All these are keywords.
Right.
Using them, if you develop any code describe, then that is called gate level.
Right.
In data flow level modeling, you have the work with operators.
Yeah.
So for everything like, to do the XOR operation, you have this operator,
Yeah.
caret symbol.
Yeah.
You have ampersand for AND operation.
Yes.
You have this, negation operator. So
Yeah.
like that, there are several operators are there in data flow.
Right.
In behavioral level modeling, we have something called, if you want to use loops, if you want to use loops.
Yeah.
So in behavioral modeling only it is possible.
Loops are also synthesizable.
Yes, yes. But you have
Okay.
to use them in a way that are recommended.
Okay.
What happened? This entire thing gone. Along with that, I thought ink will go, but that entire text of okay.
Yeah.
So then how to take off this? So draw this one. Stroke.
Yeah.
But in one shot, how it will go?
I think.
There's a problem in
Yeah.
this one note I felt.
Yeah. Maybe if you can increase the size of the eraser.
But it's that may be the solution, maybe. Okay, so here loops are synthesizable. Yes, loops are synthesizable.
Okay.
So you can use in this loops you can use uh, and then edge behavior like pause edge.
Yeah.
That behavior you can use,
Okay.
and then you can if required, yes, you have to use the operators anyway. They are required. So that in behavioral level modeling, you have the work with operators.
Yeah.
You have something called pause edge and negate keywords,
Yeah.
and you have the loops.
Right.
So some loops are supported by the synthesizer, some are not supported. Like while is there. We'll
Okay.
discuss that later on, but not now.
Yeah.
You have the for loop.
Yeah.
and you have the repeat loop.
Okay.
So like that. So now behavioral level modeling is, uh, uh, you know, is what we use in, most of the times.
Okay.
Why? Because our main purpose of having the HDL itself is to automate the design process.
Right.
Automate the design process means you have something called synthesizer. Some code you are giving to this synthesizer code, and it is
Yeah.
producing for you the netlist.
Yes.
So this netlist is what the logic and interconnection plus interconnection.
Yes.
So this
Yes.
this logic plus interconnection, if at all person knows, then why should he go for the behavioral modeling?
Yeah.
So that's what the problem with this gate level and the switch level.
Yeah.
In order to model anything, describe anything in switch level, a person must know the circuit itself first.
Right. Right.
In order to model anything, describe anything in the gate level, a person must know the required gates itself.
Yeah. Yeah.
So then there is no point of design automation there.
Right.
So that's why this is anyway not used in industry because this is not supported by the synthesizer.
Yeah.
This is rarely used,
Yes.
but most of the time industry uses this data flow and behavioral modeling.
Yeah.
So, and this is the advantage of using gate level is speed of process,
Right.
because your synthesizer is not burdened there.
Yeah. Yeah.
Already gates are known to the synthesizer means this synthesizer will not be taking much time to produce the netlist.
Yeah.
So that's the advantage. Like in case if anything possible, do it at the gate level because gate level
Right.
is supported by the synthesizer.
Yeah. And it's like
But but
the
but but this happens only 5 percentage or 2 percentage.
yeah.
Remaining 95 percentage, 98 percentage will be done at the data flow and behavioral modeling.
Right.
Structural modeling is something, a piece of code is already there. For example, you have flip-flop coding.
Yes.
You just make use of this code and you produce a counter here.
Okay.
You don't develop the counter logic.
Okay.
You just use flip-flops in a way that are required to produce the counter behavior.
Okay. Okay.
So that is called the structural modeling.
Uh,
For example, you wanted to have the 4 by 1 mux,
yes.
but you don't develop the 4 by 1 mux logic. You already have the 2 by 1 mux. You just
Okay.
use and in a way that is required to be connected, you connect
Okay.
just to produce the
So
4 by 1.
okay. So I'm using other codes together somehow to interconnecting it to make a new logic.
Yes, yes, yes. Just now we discussed somewhere here.
The half adder. Yeah, the half adder.
Full adder using two half adders.
Yeah, to a half
We
adder.
are not actually generating the logic of the full adder. We are interconnecting in a way that can produce
Right.
full adder functionality.
Right. Right.
That is called the structural modeling.
Okay.
In,
One question.
Mhm.
In this thing that you have written code synthesizer and then netlist, after synthesizer, we get bitstream or we get netlist, or what's the difference?
We get netlist. Difference is, I will tell. Uh, See, what is first of all netlist? Netlist is, listen, logic gates plus their interconnection.
Yeah.
That is what the netlist is.
Yeah.
Now, just because you have this one, your design task is not done. Design task is just done
Yeah.
20 percentage.
Yeah.
Just having obtained, having written a code, a synthesizable code. The code means not every code is synthesizable. You
Yeah.
have to write a synthesizable code and your synthesizer tool. This synthesizer tool will produce the netlist.
Okay.
This netlist, what it will contains means it contains the logic gates plus their interconnection.
Okay.
So at that point of time, you have done your work only maybe 10 percentage, not even
Okay.
the 20
Yeah.
percentage.
Yeah.
Why? Because from here the things will be different. Like you can take FPGA approach or you
Yeah.
can take the ASIC approach.
Okay.
Actually, even before, even not reaching the netlist, actually, at synthesis, while you do the synthesis process, there only you decide actually which approach that you want to adopt. Whether
Okay.
even before here means here we should decide like whether we have
Yeah.
to go for the FPGA or ASIC
Yeah.
before giving to the synthesis process only we decide.
Okay.
If you want to adopt the FPGA approach, then this entire flow is different actually.
Okay.
For example, you have the already one vertex 7. In that,
Okay.
again, families are there. One, two, three, several families
Yeah.
are there.
Yeah.
So among these several families, let's say you are taking vertex to second family, then that is what
Yeah.
the setup you do here before synthesizing. You set
Okay.
family that you are, in the family which
Yeah.
device you are choosing, everything you set here
Right. Before the synthesize. Yeah.
for the synthesis.
Yeah.
Then you perform the synthesis.
Right.
Then only the netlist is generated.
Okay.
In ASIC also same like that only. Before performing the
Yeah.
synthesis itself, you take the standard cell library.
Right.
Then you perform the synthesis.
Yeah.
So then this netlist is called the standard cell based, that
Yeah.
not FPGA based.
Yeah.
So what was the
And
question?
the bitstream and netlist difference.
Bitstream is related to the FPGA. It's a long process. Like I said, na, you set the family here
Yeah.
and you perform the synthesis.
Right.
So then what is generated is lookup tables, block RAMs,
Yeah.
and any DSP slices if you are using on chip means on this FPGA.
Yeah.
So them if you are making use, all that information will be generated after synthesis.
Right.
So even to do this synthesis here, we require to give the what we call constraints file.
Yeah.
This constraints file will have, there are two types of constraints. So one is pin constraints, the other is timing constraints.
Yeah.
Again, we are deviating from the actual subject. The actual subject is very long.
Yeah. Right. Yeah. I know.
We are getting into the this implementation discussion.
Yeah. FPGA capability.
But okay, we wrap with this a little.
Okay.
So constraints are kind of like pin constraints are there, timing constraints are there. In
Yeah.
timing constraints, you define your clock and any latency, any jitter, all that
Yeah.
information.
Yeah.
In the pin, in the on the FPGA to like which IO pins you are actually configuring.
Yeah.
That information you will give, and then you will get the all this information. Then there is a flow of PNR, place and route PNR.
Yeah. Yeah.
So in this PNR flow, you have this implementation part. This is called implementation part. This
Yeah.
implementation part, if you run, then you generate the bit file.
Yeah.
This bit file is what used to configure the FPGA.
FPGA. Yeah.
And but if you talk about the application point of view, then you also have to develop the C code.
Right. Yeah.
This C code plus this hardware, both we will generate a separate file.
Okay.
That file is actually going to the FPGA. Then you
Okay.
don't call it as FPGA, you call it as a SOC.
Okay. So in the SOC there is
Zinc,
the
zinc is there. Zinc is a SOC. You have PS programmable this system PL programmable logic.
yeah,
This is your CPU.
right.
This programmable logic is FPGA part.
Okay.
So that is different story. We'll stop with this.
Okay, yeah, fine. Are we doing any Verilog code today or just the theory part little bit today?
Just a minute, time. We'll do the Verilog part.
Okay.
So now this is coming to the mixed level.
Yeah,
You can mix any of this, all of this also you can mix, write a Verilog code, or
right,
only one flow also you can adopt.
right, right.
If you mix any of these flows, then that is called mixed level.
Okay.
So that said, if you go to this switch level modeling, as I told now, these keywords are there.
Yeah, yeah.
So these keywords are there, but this is, you know, I don't know whether required or not for you.
Yeah, I don't think.
I don't know that you have to check out with your university syllabus requirement.
No, 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 no. I don't think.
Okay, because that's how you code actually.
Right.
So
Yeah.
this you person must know this circuit.
Right. Yeah.
So then we move on to this. We talked
Like.
about something here about uh, few general things we'll discuss. So in Verilog HDL, you might be knowing already that we use this slash for comment,
Comment.
single line.
Yeah.
So multiple line means this forward slash,
Yeah.
asterisk, and then multiple lines. Then where you want to end that comment, there asterisk, then again forward slash.
Yeah.
So this is for single line. These are for multiple lines.
Yeah.
That is one thing that you have to keep in mind. The other thing is uh, all keywords are lowercase or lowercase. That you have to keep in mind. Lowercase. So this any module, anything that you describe that will start with the keyword module
Yeah.
and it will have end module.
Okay.
So this end module, you shouldn't be making a mistake thinking that end space module.
Okay.
So there is no space,
Yeah.
without space end module.
Yeah.
Then module space will come here. Then you write the module name.
Okay.
So
Yeah.
this module name is a user defined.
Yeah.
User defined, but some protocol rules are there, like it shouldn't be starting with dollar $HA,
Yeah.
or some tools even give error, like if you start with numeric
Like.
to H.
Yeah. The like basic C plus plus variable name rules.
So we have to start with like alphabet
Yeah.
or underscore also permitted.
Yeah.
So, and moreover, there shouldn't be any space in the module name also.
Right.
You cannot have like a half space adder like that.
Yeah.
You have to have
Yeah.
underscore.
Right.
Then open the parenthesis and put the port list here.
Yeah.
And then close the parenthesis, terminate with a semicolon.
Okay.
And then here you will have the type declaration.
Right.
So this type declaration, what you do here is this port list, let us say A, B, sum, and carry out these variables to which type they belong. Let's say
Okay.
AB belongs to input type,
Yeah.
and sum and carry out they belongs to output type.
Yeah.
So this input is a keyword, output is also a keyword.
Right.
So the as said, all keywords are lowercase. So input lowercase, output is also lowercase.
Yes.
Language has taken several amendments in the 1985. It was like that, like port list will be there.
Yeah.
and you have the type declaration here.
Yeah.
But according to language amendments taken place in 2001, then we can write like a module and the module name. Here itself, we can write input A,
Yeah.
comma, B, comma, output, sum, comma, carry out, and the semicolon.
Yeah.
So that way we can write according to that latest language amendments.
Yeah.
And in that case, you don't require to declare here.
Right.
So then other thing is we have something called data type. So this
Yeah.
data type here, if you look here we have net data type is there and register data type. So
Okay.
net register data type, but this register name is according to 1985 language standard. According to 2001 standard, this register has become
Okay.
variable data type.
Okay.
So now, from now on, we supposed to be using, there are two data types. One is net data type, the other is a variable data type.
Okay.
In net data type, we have these many things. All these are keywords. Wire is a
Okay.
keyword. TR is a keyword. War is a keyword. Trior is a keyword.
Okay.
WAND, triand, tri-reg, try1, try0, supply0, supply1.
Okay.
So all those are the keywords actually.
Keyword. Yeah.
So among them, wire is synthesizable, war, WAND are synthesizable. I have to check this. I forgotten trior, triand are synthesizable or not. I check them.
Okay.
And anyway, supply 0, supply 1 are not used because they are part of that switch level model.
Okay.
So coming to the let's say our some hardware this black box BB black
Yeah.
box, it has got like this kind of representation, and another black box BB2 BB1, it has got like this representation. So what
Yes.
is the difference here is this kind of representation is for scalar.
Okay.
If you put this slash,
Yeah.
then that is for vector.
Okay.
So it means that this input is more than one bit.
Okay.
If you put like this, a single bit.
Okay. Okay.
So now let us say you have something where you have to give more than one bit, means you bit size also required to be shown like this.
Yeah.
So it tells that this line is of 3 bits.
Right.
And let's say the name of this line is A. So
Okay.
now let's say that is wire type. So since size is 3, there are
Yeah.
various ways. One is like this you can show. The other is
Yeah.
like this also you can show. The
Okay.
other is -1, 0, 1. This also you can represent like this also. So it means what? This side is MSB,
Yeah.
this side is LSB. That is the meaning. This is
Okay.
MSB, this is LSB. So
Okay.
in this case, A of 2, A of 1, A of 0. In this
Right.
case, A of 0, A of 1, A of 2.
Yeah.
In this case, A of -1, A of 0, A of 1. And
It can be anything, right?
can
It
be
can be
anything, but
the
it should match this size.
can it be like square bracket 10 that the dot and then
Yes, yes.
12.
10, 11, 12.
Oh, okay.
Yes, this is also possible.
Okay. Okay, got
So
it.
what is recommended is human psychology accepts this kind of thing.
Yeah.
because human is MSB means some high value
Yeah. Yeah.
like this.
Yeah.
LSB means some lower value.
Right.
When you compare with this
Yeah.
number, this number must be lesser.
Yeah.
So that's
Yeah.
why human is, according to human psychology, this is most preferred. It is recommended way of writing. That's what majority of the books
Yeah.
says.
Yeah.
And they
Okay.
say avoid like this fancy kind of, thing.
Yeah. Yeah.
So that is about that. And in some of the cases, we may require to show like this also. Like this is having some depth here, like 0,
Yeah.
1, 2, 3, 4, and each is having capability of, let's say, 8 bits. And
Okay.
this entire thing we are calling it as a.
Okay.
So in that case, this is, let's say, data type is wire, and the size comes first. This size comes here, that is 7
Yeah.
colon 0. And the name comes later, and then the depth will come like here, 0.
Okay.
Okay. Okay.
Okay. Yeah.
So it means what? This is A of 0 of size 8
Yeah.
bit.
Right.
A of 1 like that, A of 4 till A of 4.
Yeah. Yeah.
So like that, A of 4.
4.
And every this index is having
Row
of
is having
8 bit.
8 bits. Yeah.
Like that. That is the meaning of this one.
Okay.
Okay.
Yeah.
Now, uh, coming to the uh, no, this data type here.
Yeah.
In case of this one here, as I said, there are two types. One is net data type, the other is variable data type.
Yeah.
In this variable data type, we have something called integer, something called reg, something called time, something called real time.
Okay.
And we use in the coding this integer reg, they are used to in the description part. These are used time and real time are in simulation we use.
Right.
And this real is some numbers like this 3.14 like that.
Okay.
This is not, this is, I had to check whether this is supported by the synthesizer or not.
Okay.
According to my so far memory, this is not supported.
Yeah.
So then mostly we use this for describing like, for in synthesis.
Yeah.
Synthesis.
Yeah.
This one and this one is for simulation. The
Okay.
simulation time, like your simulation time is proceeding from 0 to
Yeah.
some time, let's say 100.
Yeah.
You want this to display on the console, and so what time, like, simulator, how it is proceeding.
Yeah.
So you can use time or real time. Real time, what it does is, like, let's say you have time of 9.7.
Yeah.
Such times it will help us to display.
Uh, but in simulation also we use reg, right?
No,
And
these are used in simulation also, no problem.
okay. Okay.
But they are supported by the synthesis.
Okay.
Integer is actually used for the loop index.
Right.
This is used for the loop index only.
Okay.
Reg is the main thing.
Right. Yeah.
So these are used in behavioral modeling.
Yeah.
These are compulsory. This data type is compulsory in the
Yeah.
behavioral modeling. So behavioral level modeling data types, that's what you can think of, you can keep in mind.
Yeah. Yeah.
In behavioral level modeling, variable data types are must.
Right.
There are 5 types. One is the integer, second is the reg, time, real,
Yeah.
and real time.
Yeah, I've only heard about integer and reg. Time, real time, and real. I haven't heard.
I will demonstrate that.
Yeah,
How it is used in coding in
yeah,
test benches, I will demonstrate that.
yeah. Okay, okay,
Coming
perfect.
to the net data type, mostly
Yeah,
we use wire.
yeah,
And then we have here, uh, this is WAND and WAR, they are supported by the synthesizer, but we rarely use them.
okay.
And this net data type is mostly used in all of the, like, except this behavioral level modeling,
Yeah,
we use in gate level,
yeah,
and this is data flow level modeling,
yeah.
we use there.
Okay,
So in behavioral level modeling, only variable data type, what I mean is variable data type, like in a behavioral modeling, we have something called procedural constructs are there.
yeah,
These procedural constructs are of two types. One is always,
yeah,
the other is the initial.
yeah,
I will talk some other day about this usage, but for
yeah,
now, inside this always or inside this initial, anything that you want to assign, that is, left hand, left
yeah.
side, that must be of variable data type.
Okay,
But right hand side, like you are assigning A to B, I mean B to A,
yeah,
then A must be of variable data type.
okay,
B can be net or variable.
okay.
But this one left hand side must be variable data type only.
Yeah, yeah,
Inside this always, inside this initial.
okay.
If you are using some variable to which you are assigning something being in always statement or being in initial statement, then
Yeah,
compiler will throw error.
okay.
Okay.
Yeah,
I will demonstrate whatever I'm talking. This is vague idea I am giving you just
yeah,
to,
yeah, yeah, understood.
fast track, like you can wrap very early.
Yeah, yeah,
Every bit. See, these are in textbook. Several things they have given. For example,
yeah,
uh, entire memory cannot be assigned. All that.
yeah.
Instead of going this way of terminology, I am just talking like that.
Yes, yes.
Then I think I'm tired now. Uh,
Okay, yeah.
I cannot continue with the demonstration.
Yeah, it's fine.
So what I will do is